In this super tiny domain, atoms are giants, and matter behaves mysteriously. This is the microscopic world of quantum science. These are its explorers, and this is the story of Sequim, the Center for Integrated Quantum Materials, an extraordinary effort to tap the potential of quantum forces to reshape our future. The Center for Integrated Quantum Materials, Sequim for short, is a consortium of institutions funded by the National Science Foundation and headquartered at Harvard University. For more than a decade, Sequim has been probing the frontiers of quantum science, led by its director, Robert Westervelt.
A number of us were interested in what we call quantum materials, which are materials that had recently been discovered and have extraordinary new capabilities that can be turned into new products. Some of the areas that quantum can have a big effect is in processing data. It's possible to solve problems that you couldn't solve otherwise, and also transmitting data from one place to another. Quantum materials will have a big effect in electronics and go beyond what's possible with regular materials.
Sequim includes some of the world's leading quantum researchers, but it is far more than a collection of top scientists. It is also a dynamic idea exchange and an opportunity for young scientists to learn their craft.
The students are the most important product.
So these are the two things that control the position of the photodiode.
Okay.
Howard University's Tina Brower has directed the Sequim intern program from its inception.
Let's take a look at that sample.
A quantum scientist in her own right,
Okay, let's welcome our next speaker.
Brower
Mr.
recruits, mentors, and manages virtually all aspects of this unique undergraduate program.
I would like to thank Dr. Brower, who has definitely pushed me out of my comfort zone this summer.
Sequim has worked with over 100 students over the last 9 years.
At the core of the program is an intense 10-week summer session at Harvard and MIT.
We are going to decide how many solutions we are going to have, how many samples we are going to need.
The interns are assigned to research teams, trained in high-tech lab activities, and given research assignments they must complete and present to the group.
So we selected strontium titanate, which undergoes a surface reconstruction at 950 degrees Celsius.
These presentations are a long way from where the interns started.
My name is Desvon Drummond. I am originally from Kingston, Jamaica. I knew absolutely nothing about quantum materials or anything quantum related. All I knew was that quantum was the new buzzword.
My name is Christian. I'm from El Salvador. The reason I joined this program is because it's one of the best opportunities I ever had in my life. Monolayer of a material that is literally one atom thin.
And for virtually all the interns, their quantum leap has paid off.
They start off maybe a little bit intimidated, but in the end, when they're giving their presentations, I could just see how proud they are of themselves.
Thank you for your time. I'll be taking any questions.
The students are not only taught quantum theory,
You'll basically turn that until you hear a click. Keep going.
they learn to operate complex, costly devices that do not exist at their home schools.
All right, so then if you hand that to me.
For this, they need and get plenty of mentoring.
That looks like a great sample.
Yeah, it does.
The mentors are typically graduate students and postdocs. They take it very seriously. They develop a real relationship with the interns.
Thank you for your hard work this summer.
But it can still be a very daunting experience.
Starting out
working as an intern in the Sequim labs where, you have substances such as liquid nitrogen and helium. It was a little bit intimidating because you had to go through rigorous training to make sure you don't turn this dial too high and then cause, the fire alarm or smoke detector to go off or something like that.
You don't really know how the world works until you step out and start doing some real world stuff and understand how science works.
When I interview students to join the group, I warn them that in my group we do a lot of exploration and discovery. So if they're afraid of going into the jungle, and start, exploring, uncharted territory, they should not join.
When you're an undergrad, those are your three options. Graduate school to go to industry, graduate school to go to academia, or directly in the industry. It just depends on what you value.
Brower also arranges career workshops for the interns, providing guidance on how to apply to graduate school and what to expect from a job in industry.
There's no one right answer. It's what works for you at this moment in your life.
At the end of the day, you have to put the work in, right? And I don't care what avenue that takes.
Sometimes it's better to know what you don't want to do to figure out what you do want to do.
Another wire connected to the back gate underneath the transistor.
There are also science communication workshops that former interns still value highly.
I was required to stand up and present all of this information in front of, PhD students and doctors and Harvard University graduates. I just look back at, younger me in those moments where I didn't think that I could do it. And if I could do it one time, I could do it again.
In 2004, two University of Manchester scientists took a piece of graphite, the material in a pencil, and began to peel off surface layers with Scotch tape. They stuck and unstuck the graphite-laden tape until
some pieces of graphite, 1 atom thick material, were left.
At 1 atom thick, graphite was now a material called graphene. It's the lightest material we can see under this microscope.
This is 1 atom thick, so it's the thinnest material that exists and that it will ever exist. There's nothing, you cannot make a material less than 1 atom thick.
Graphene is actually a honeycomb of carbon atoms that, despite its wispy appearance, is super strong and can even conduct electricity. But a more extraordinary property emerged when Pablo Herrero put two graphene sheets together and twisted them.
You would literally see something like this under an electron microscope, which has this chicken wire structure, okay? Then we can take another sheet of graphene, place them on top of each other, and then rotate the angle between these two graphene sheets. This sort of soccer ball looking things that you see here in this sheet, that's called a moire pattern.
Remarkably, the twisted sheet's moire pattern had a dramatic effect on graphene's conductivity.
The electrons in a single graphene sheet, they go super fast. When you put two sheets and you twist them 1.1 degrees, they slow down tremendously. They almost go down to zero. And that extreme slowdown of the electrons has dramatic consequences for their electronic behavior.
This electron slowdown means the moirade graphene had become what's called a superconductor.
One way to get energy or information from point A to point B without loss is with a material called a superconductor. In a normal material, each electron is kind of moving around doing its own thing, and it can scatter off of other electrons. And when it scatters, that is when it loses energy to heat.
This scattering results in a 10% loss of energy inside the copper wires that carry much of the electric current in our homes and businesses.
But in a superconductor, the electrons pair and move collectively, which allows them to carry energy without loss.
This is exactly what happens in the twisted graphene.
That looks good, right?
I think that looks good.
I think that's ready. Yeah, okay.
And since superconducting materials could improve virtually all manner of electronics, many researchers are experimenting with super-thin graphene and other two-dimensional materials to see if they can create novel quantum electrical devices. In most quantum labs, you'll find tanks of liquid nitrogen or helium. That's because only at temperatures as cold or colder than 450 degrees below zero do electrons slow down enough for researchers to control them. So they need the freezing properties of liquid nitrogen, helium, or both in order to do this.
Okay, we're going.
We cool our materials down to really, really low temperatures so that we can measure the interactions between electrons or between electrons and other things to have a better understanding of what's going on.
Isabel Finney and Andres Mier Valdivia are graduate students in Philip Kim's lab at Harvard.
Let me check the second one. Let me check 5.
Though young, they've been working on two-dimensional materials for several years now.
Let me take these resistors off.
They understand the equipment, the processes, and the information these experiments can provide.
I like being able to take different materials and learn about them to access the types of physics that you can't access in the regular world.
Today, they are exploring a material called niobium nitride, a metal at room temperature, but a superconductor at super cold temperatures. After depositing the niobium on a silicon wafer, they carefully attach tiny wires that will conduct the electricity. They then place the sample in liquid helium, introduce electricity, and measure the result.
What we want to do is to see if the electrons can move through completely without any sort of drag or resistance on them.
If there's a voltage drop to 0, it means there's no electrical resistance.
The needle does drop sharply, showing 0 resistance.
And that means it's superconducting. It tells us that the niobium nitride is of high quality.
And if it's very high quality, we can proceed to use it in other experiments.
Experiments that test the quantum properties of new materials and devices are being performed every day in labs around the world. And many require this environment of extreme cold. Because right now, without the cold, quantum effects are harder to produce, measure, and control.
And so even if we have a material that can conduct electricity without loss from point A to point B, if we have to refrigerate that material in order to get it to work, then we're not actually saving energy. So what we're looking for is a material that has this property of lossless electricity transport at room temperature.
It would be better if we had these capabilities and these behaviors of matter at room temperature. That would make them a lot more appealing for a broader set of applications. We do not know yet how to do this.
The holy grail is to discover a room temperature superconductor. So if we see a material that's got 0 resistivity at room temperature, then we're going to Sweden.
In the microscopic world of quantum research, one of Sequim's most important members is David Bell.
So if we look at a 2D material and we look straight down, each of these white dots is actually a single column of atoms.
Bell is often asked to analyze the precise atomic structure of quantum materials.
This is an ultra-high resolution aberration-corrected electron microscope. There are only 2 or 3 of these microscopes in the world. These are materials that are made by various researchers in Sequim. They are very novel materials that have never been seen before. We put in the electron microscope to understand what the structure of the material looks like, how it's constructed. This is a gold nanoparticle on a very ultra-thin carbon film. The microscope is so sensitive that even as I'm talking, the sample is moving because we're magnifying 10 million times. Even my voice is enough to make the sample move a little bit. And if you can see the little white and dark dots in the sample, they are actually gold atoms sitting on the surface of the carbon.
Performing such highly intensive and time-consuming work is only one facet of a typical David Bell day.
Hi, Kevin.
Hey, how you doing?
He also helps manage operations at Harvard's Center for Nanoscale Systems that comprises 2 entire floors of this long building. CNS contains a stunning array of some of the most advanced scientific equipment to be found on any campus, anywhere.
This is one of the corridors of CNS, the Center for Nanoscale Systems at Harvard. Here is the nanofab area, or the clean room area. You are the dirtiest thing in the clean room. When you go in, you shed skin and hair. So you have to wear a bunny suit, like this person right there, who's waving at me. And we have these yellowy and orange lights here. This is to stop things getting damaged by white light. The nanofab is like Intel when they build chips and things like that. Although we're not building devices or chips for production, the devices that are made in our nanofab are research devices. So now we're in the basement, and CNS has equipment in the basement because it's the most vibrationally isolated area. We have a lot of junk around here, of things being upgraded or replaced. We have electron microscopes, we have optical microscopes, we have scanning probe microscopes, we have X-ray microscopes. We have literally the entire range of microscopic technologies to look at all different size ranges, from big things to atomic size things. CNS has been an absolutely great benefit to research in the quantum realm. Image anything you want and basically analyze anything that you bring in to CNS.
Using this mysterious-looking array of laser lights, mirrors, and various machines hiding in the dark, Harvard's Neil Sinclair is trying to capture a single photon of light and encode it with information.
A photon is an indivisible amount of light, so it's the most fundamental quantity of light that exists.
And they are literally all around us.
This light that's illuminating me right now has billions of photons in it. You could think of billions of photons per second as hitting me and then reflecting off of my face and going into the camera.
But if he can somehow isolate and capture just one photon, Sinclair could utilize what we now understand are a photon's quantum properties.
If you direct a photon to, let's say, a window, your photon can go through the window. There's also a chance that that photon can be reflected off of the window. The point is that the photon can't be split into two. It can't go, half of it go through and half of it be reflected. So what ends up happening is that it's a complete quantum mechanical uncertainty as to whether the photon is transmitted or reflected from that window. And that's called quantum superposition.
Being in two states at once, transmission or reflection, gives photons the quantum properties of what are called qubits that may one day revolutionize computing.
You have now two distinct paths: transmission or reflection, 0 or 1. So now you have the basic elements of a computer.
For some time now, people have wanted to make a computer that, instead of using classical bits of information, that is a 0 or a 1, to use qubits of information that can simultaneously be a 0 or a 1.
So the idea is that you have a multitude of potential calculations that you can perform at the same time.
So a quantum computer, it's essentially crunching data on very many possibilities, whereas classical computer does it one byte at a time.
The electrons coursing through today's computers can also become qubits, which would make them an essential component of quantum computing.
What quantum mechanics allows is an electron to be just like the photon being transmitted or reflected. If you put an electron in a magnetic field, it can take two possible values: spin up, pointed with the field, and spin down, pointed against the field.
As it turns out, one of the best sources of qubits lie inside of diamonds. A sparkling clear diamond is actually a dense lattice of carbon atoms. Sometimes impurities like nitrogen atoms invade the lattice, and when they do, a clear crystal diamond will pick up a hue. In this case, the nitrogen atoms make it appear yellow. What you cannot see is that the nitrogen atoms have displaced some of the carbon atoms. And when they do, they leave holes called vacancy centers that contain trapped electrons from the original carbon atoms. And these electrons can be in a superposition of spin up and spin down, making them useful as qubits.
Some of the more promising quantum memories are electron spins in diamond.
In this experiment, Sinclair is using lasers to test the quantum properties of vacancy centers in a sliver of diamond.
These are lab-grown diamonds cut from a bigger diamond and polished down to this square here.
Researchers prepare the diamond sliver with oval-looking shafts. They then implant a silicon atom between two of the shafts, creating a vacancy center. When the silicon atom is excited by lasers, it will emit a single photon that will reflect off the mirror-like surfaces of the shafts and out of the diamond.
Once the diamond defects are happily in their diamond, we'll shoot a laser through these mirrors, excite it, and then we'll measure the light that's emitted off of the diamond.
As the laser repeatedly strikes the sample, suddenly,
we see a burst of light. What's happening is we cause diamond defects to emit single photons. And we're studying how well those defects can do this consistently.
Since individual photons acting as qubits can also encode information, what we see on this graph may one day become a pathway to quantum computing or even a quantum internet. In fact, right now,
this photon can be captured and sent via optical fiber over a very long distance.
We currently send non-quantum photonic information through fiber optic networks that facilitate telephone and internet communications. But a key challenge has been to keep that information safe from hackers. And quantum communications can offer a way to do that.
So if somebody were to eavesdrop and try to listen out in our communication, they would immediately be detected.
That's because if you send qubits in superposition and someone hacks into the stream to capture their information, the quantum state will immediately collapse, and the information will revert to classical zeros and ones, thus alerting the communicating parties to the hack. Today, to try and thwart hackers, computer data is encrypted with extremely complex mathematical formulas. But if hackers had a quantum computer, there's a very good chance they could decipher almost any code. In part, that's why the race to develop quantum computers is already on. Although prototypes are up and running in the US and around the world, these computers are still in their infancy and currently can only perform specialized tasks. But the hope is that one day they will be able to do data processing and complex computations far faster than current computers. However, there are major hurdles still to jump.
Quantum computers do need to be very, very cold, which is very expensive in terms of money and energy.
And they are also extremely large.
It's ginormous beast.
But will they follow the trajectory of classic computers and get smaller and better?
It will be some time in the future before that happens.
I do hope that I can observe that progress in the quantum science, including quantum computing, for example. Whether that will happen within my scientific career or within my lifetime, this is a way to see. But I sense that it may. It may.
As an African American woman, I understand what it's like to show up in a lab and know that I'm just there to check a box. But I also know what it's like to show up in a lab and someone is interested in my development.
Yeah, I see it.
And that's what we're committed to.
That the Sequim community is committed to student development, teamwork, and inclusion is there for all to see.
We're going to start by going around the room today and just giving a short update on what we've been doing for the week, challenges.
For me this week, it's a pretty good week.
Been getting the room ready, so talking a lot with Connie.
I love the fact that my team runs the gamut of ages. I have a senior scientist who is my peer, I have postdocs, I have graduate students, I have undergraduates, and I have high school students. Sort of a mentorship ladder where everybody is helping each other out and reaching a hand down to pull up the junior scientists.
There's amorphous at room temperature, and at high temperature it's gone, so you need somewhere in the middle.
Yeah, probably.
One of the things that has benefited me most directly in Sequim is to be able to interact with undergraduates from Wellesley, from Howard University, from other schools who have different backgrounds.
Bringing more people into the game is altogether a better idea.
You don't apply any voltage, but then you actually get the current out.
And this is super exciting research, and I was really thrilled to be part of many discoveries. But perhaps the most appealing part is the community aspect. Different expertise, different areas of interest, but all of us with the common passion for quantum physics and also a goal of trying to develop new technologies.
There's science that we created in Sequim that would not have existed were it not for the synergistic effect of bringing together students from a number of institutions.
That's phenomenal. So this is a calculation.
For each of the green curve.
The model for Center was to really form a community that includes everybody, to do things in an equitable way, and to help people who may not have a rich background to actually pursue what they're interested in.
Like Angela Bamtifa.
This week a lot has happened, including kind of loading our first calibration sample for the hexaboride.
She traveled from Nigeria to Howard University in Washington, where she entered the Sequim intern program and is now a PhD student in Jenny Huffman's lab at Harvard.
Angela was a little reluctant to apply to Harvard. I think she thought maybe it was not within her reach, which I was like, are you kidding?
After Jason checked the diagnostics, it worked, and that was really amazing. Very excited to set that whole thing up.
Many former Sequim interns are also pursuing graduate degrees, while others have chosen careers in industry.
When they put on their resume that they've learned specific tools in quantum, they get jobs and they're coveted for graduate programs.
Probably 90% of our students tell us that the job that they have now, quantum science, is some integral part of what they're doing.
Sequim!
My name is Tiwa Poon, and I was a Sequim intern while I was getting my graduate degree at Howard University. Currently, I am a research engineer at Lockheed Martin Space. It's my exposure to quantum physics, just the experience of going through the Sequim process of here's the project, what is our purpose and goal, and then this is what we need to do Those steps, I still use them in my current job.
My name is Brianna Pinkney Bailey, a lead spacecraft engineer with Boeing. I interned at Howard University, and then I did my sophomore year at Harvard University. No, I'm not, doping diamonds anymore, and I'm working on something totally different. But the confidence that I learned throughout that internship, I carry with me every day. And now that I got to be a part of this experience, I get to go and look back and be an encouragement to other young brown and black girls as well.
So you're preparing what? One for Raman, one for XPS, and...
Oh, and one to repeat the experiment.
Okay, great.
My name is Ashley Enriquez. I've been involved with the Center for Integrated Quantum Materials since my time at Prince George Community College. I'm trying to get this down to 0.01 millibars.
I don't know if I know a more determined young person than Ashley. She's had to overcome so much.
My daughter was born when I was 15 years old. I had to drop out of high school. By the time I was 17, I was working full-time. I did pursue my GED, and I started going to community college.
Okay, perfect.
Next month, I'm graduating from the University of Maryland College Park with my bachelor's in electrical engineering.
Now headed for graduate school, Ashley is just one example of how successful Sequim has been for its students.
Almost 90% of our interns stay within STEM. They go for STEM-related careers or STEM degrees.
We're interested in how strain can be used to manipulate two-dimensional materials and induce their properties.
100% of our community college graduates have gone on to 4-year degrees. And so I'm very proud of that.
We use a micropipette.
And for students like Ashley, who are continuing their quantum studies,
a career in quantum is excellent. If you're a student, you have to think about what's going to be hot 10 years from now, okay? You don't want to work in a field that's going to fold up and die. And the quantum is really taking off now.
And we're going to need a lot of people with expertise that will enable us to make new devices that will have important technological applications.
Today, researchers the world over are fabricating working quantum devices and homing in on better materials and designs for making them. In fact, quantum science is being applied to and benefiting more and more facets of modern life. And the Sequim team has been a major contributor to this progress, especially through their transformational approach of integrating breakthrough research with outstanding initiatives in education and training.
I think the funding by the NSF of Sequim has been an absolutely great benefit to research in the quantum realm and has actually changed a lot of our lives, to be honest. I think that there's things that we would not have done without Sequim.